I want to get back into a little bit of the logarithm stuff just because that's something to have the most trouble with.
There's really 4 or 5 things that you have to memorize to be master of logarithms. And that's it. You need to be able to convert from exponential format to logarithmic format back and forth.
Right.
And you need those 3 rules of logs. In other words, the log of the product is equal to the sum of the logs, those 3 rules. And that's pretty much it. I can't think of anything else that would be useful when dealing with logs. Yeah, that's going to cover expanding, compressing, solving log equations, all of that stuff.
Okay, so let's just do a problem, I guess.
Okay.
Log of 2, log base 2 of x plus 2 plus log base 2 of x minus 1 equals 2.
All right. So
you multiply these.
Go ahead. So what's the next line?
So it would be log base 2 of x plus 2 times x minus 1.
X minus 2. Let's put it in the quadratic format. In other words, I multiplied those 2 numbers together.
X plus x equals, no, minus 2.
Okay. Now we have a single logarithmic statement. Up here we had 2 of them. Now we have 1. And that's always the goal, is to try to get it down to 1 log statement. Whether I have a log on the other side or not. In other words, now how do I solve this? Now that I have it down to a single log statement. Put it into exponential format. That's the key. You solve log equations by the second to last step is almost always to put it into the other format.
So it's log base 2.
No, put it into an exponential format. Let's go back over and talk about
so wait,
because this is really important, that you be able to go back and forth between an exponential and the logarithmic. What's the logarithmic statement of what I just wrote on the right side of the screen?
You want me to complete it?
Yeah, how do you put y equal b to the x in log form?
Log b, log base b equals, no, y equals x.
Okay. Now take this and put it back into this format.
So that means
you can do it. Yeah, how you memorize it is up to you. I use a little technique that I kind of like, and that's the number on the far left raised to the power of the number on the far right is equal to the argument. In other words, the next thing I would write would be b to the x equals y. Okay? That's just the pattern I use always. There's only one problem with that pattern, and that is if I switch it up like this, then it's no longer the number on the far left. In other words, it's the base to the exponent equals the argument. The base to the exponent equals the argument.
And the exponent is x.
In this case, yeah. Now let's take this logarithmic expression over here and let's apply the same concept.
So x plus x minus 2 to the second.
No. Let's go back again. It's the base raised to the exponent is equal to the argument. What's in the parentheses I call the argument.
Okay. So it's 2 to the 2. 2 to the second. 2 to the second equals
the argument.
X squared plus x minus 2.
Now, this is a quadratic that we can solve. Okay?
Right.
Let's proceed to solve it.
We could root both sides.
No? That's not the way you solve typical quadratics. What's the first thing you think of when you're going to solve a quadratic? Put it in standard format, which is with 0 on one side of the equation. Whenever you have both an x squared term and an x term, you're going to need to solve it that way, which is put 0 on one side of the equation.
Okay.
Standard
so x squared plus x minus 6 equals 0.
Okay. Now, if you didn't have this x term, if I just had x squared minus 6, well, I wouldn't need to solve it like that. I could leave the 6 on the other side, take the square root of both sides, and come up with a solution. But when you have the x term in there,
right,
you always have to solve a quadratic like this. And the first thing we want to try to do is factor it. It might be factorable. If it is, it saves a lot of time, so let's factor it. If it's not factorable, then we have to apply the quadratic formula to solve it. But this is factorable. What are the factors?
X plus...
Has to be opposite signs. It's the only way you can produce the minus 6.
Okay, so x plus 3, x minus 3.
Yeah. X plus 3, x minus 2. These two numbers have to be factors of this constant.
That's what I meant to say.
Okay. So we get x equal minus 3 and x equal 2 as our solutions. And now, whenever you have a logarithmic equation that produces a quadratic that produces two solutions, almost always one of those solutions is going to violate the domain, and so you throw it away. It's extraneous.
Because you can't have a negative...
You can't even have 0. You cannot have an argument of 0 or negative numbers. The argument always has to be positive.
So 2's the answer.
Yeah, in other words, this one we throw away, and x equal 2 is the solution. And that does not violate either argument. And once again, I say this to all students, but never test your domain in that. This is a manipulation of this. It's not the same thing. It's very, very possible that you'd be violating one of these domains, and yet you're not violating this domain. In fact, this is one of those cases. If I plug in minus 3 over here, I get 9 minus 3 minus 2. I get a positive 4. So it would not violate this domain. So make sure
it's only about the original domain.
What's that?
It's only about the original domain.
Only. Which tells you a little something. It tells you that these two are not exactly equivalent. In other words, we have these rules of logs that allows us to do these things, but they're not equivalent. I could have a minus 3 here. I cannot have a minus 3 up there.
Right.
All right.
So then we have like population growth, which I think I'm good at. I just gotta...
The reason population growth is a log question is because your variable is usually in the exponent.
Right, it raises exponentially.
Yeah, well, your variable is usually in the exponent. In other words, P equals e to the RT. That's usually the variable you're trying to solve for. E is a constant, but population growth is continuous compounding.
Right.
And so whatever the population, let's say I think I need a starting population. Yeah. P sub 1 or P sub 0 or A sub 0 there. But your final population is going to be your initial population times e to the rate of population growth times the number of years you would have it. So give me the problem, we'll set up the equation, and then you'll see that you have to use logs to solve it.
The initial size of a culture of a bacteria is 1,000. So that's immediately 1,000 plus, and then
not plus.
After 1
time.
After 1 hour, after the 1 hour, the bacteria count is 8,000. So find a function that models the population after t hours.
All right. So what we have is 8,000 is what it grows to. There's what it started with. It's e to the r, which we don't know, but we know t is 1. So we have to solve for r to come up with this equation. And that will be the rate of growth. Okay? So let's solve this equation right here.
So you could divide 8,000 by 1,000.
Okay.
So 8 equals e to the r. And you could divide 8 by e, can't you?
No, because this is part of the exponential. This is what I'm saying is that
okay, so you need a logarithm.
This is now an exponential expression. It's no longer an algebraic expression. We don't have any algebra to solve it. So when you try to divide both sides by e, you're trying to solve it with algebra. You need to apply.
Okay, so I'm going to switch the order, and I'm going to bring it down. So I'm going to do r log e, or ln.
Okay, so first thing I'm going to do is take the log of both sides.
Right. So ln equals, r ln equals 8 ln.
Actually, this part of it, okay, here, let's do it step by step, just so.
Yeah, r ln equals 8 ln.
And what's ln of e?
1.
Right. And that's the beauty of using natural logs when you're dealing with e, is this always comes out to be 1.
Right.
Okay, so r equals natural log of 8. So now, what is our specific formula for this particular Petri dish?
So the initial formula is P equals 1,000 E to the ln of 8.
ln of 8 times t.
Right.
In other words, t is the most important variable there. Ln of 8 was merely the rate of growth.
Right.
Of course, that's pretty important too. The higher the rate of growth is, the faster the log is going to grow. Huh?
Now apply the formula, find the population after 1.5 hours.
Okay. So now we substitute 1.5 for t. So
1,000 e the ln of 8 times 1.5. So I'm going to do that on my calculator.
Your inspire?
84.
Okay, make sure you get it in right. In other words, I can see that this might be a little tricky. 1,000 times e, and use the letter.
E, the letter will bring e?
Well, there's a letter e on your TI-84.
Like the green, like the alpha letter?
Yes, like pi. Okay. In other words, don't use 2.71. Use the true value of e, or as close as your calculator is going to approximate it. and then raise that to the
Where's that? ln of 8
times 1.5. Make sure all of that's in the exponent.
It's giving me 0.
This is twice now that I need that virtual TI-84. I haven't gotten it yet.
Oh, wait. I think I'm doing something wrong. I'm going to do 1,000. Should I raise E to ln 84 and then multiply it by 1,000?
Sure, that's probably a little easier.
E.
And it's not it's e to the natural log of 8 times 1.5, right? It's 1.5 hours?
Yeah.
Okay. Notice I could rewrite that. I could put that 1.5 in front and then move it to an exponent. So it's actually the natural log of 8 to the 3/2 power.
It's giving me 0 again. I think E in this calculator isn't E. I think it's just a letter, like a variable.
You may be just using the letter. The E is the second key. Hold on, let me show you where it's at. I still have my TI-84.
Is it?
E is above the division key. That E.
Oh, okay, I found it. I was using the letter E.
Yeah.
So E, okay, let me try this again.
Okay.
1,000.
Ah, you were using the green E. Yeah.
I'm using the green E. 1,000 E to the natural log of 8 times 1.5.
Now you may need an extra set of parentheses around that.
I got it. I got the answer.
Okay.
So the answer is 22627.417.
To multiply it by 1,000?
Yeah.
What'd you get for an answer?
I got 22,627.417.
Okay, I guess that makes a little bit of sense. In other words, if 1,000 grows to 8,000 in 1 hour, well, that 8,000 in another hour would grow to 64,000, right?
Right.
So in a half an hour, growing to 22,000 certainly is a ballpark figure. So that kind of verifies that it's as close as I could have approximated it almost. Means you probably got it in there right.
Now it's asking me, when will the population reach 15,000?
Okay. So for the population, we've got our general formula, and that's really all we need.
So 15,000 equals 1,000 E to the ln of 8 times T.
Times T. Is that what you said?
Yeah.
Okay. Now, solve this. Right off the get-go, the only variable in this problem is in the exponent. Okay, so you know that you got to use logs to solve it. Always look for that. But not right off the get-go. You can use algebra up to a point. You can use algebra until we get this isolated.
So divide by 1,000.
Mm-hmm.
Okay, so that leaves us with
15.
15 equals E to the ln of 8 times T.
Right.
Then I need a logarithm.
Natural log.
Right. So I'm going to flip it. Ln of E. Well, 8. Wait, this is a little confusing. So ln 8 of T, ln E.
Yeah, it's not of T, but it's ln 8 times T times ln E.
It's ln, it's not base 8 though, right? It's just ln 8.
Correct.
ln 8 times T.
The base on ln is E. In other words, this is what ln means. It means log base E.
Right. So ln 8t ln e, I have parentheses, but I don't think it matters,
No.
equal ln 15.
Yeah, and this always goes away because that goes to 1.
Right, so that's 1. So ln of 8t equals ln 15.
So what's
So I need to find, do I need to find the value of ln 15 and then?
No, they're just numbers, and in fact, that's the most accurate number. You can't give me it more accurately than that. So
T is
this divided by what?
By ln of 8.
Right, and that's your answer. I mean, in this particular, when you're dealing with these kind of problems, they generally want a number. So you can put this into your calculator and come up with a number. Since they ask for number of years, did they ask for it rounded to anything?
No.
Okay.
This
would be a very acceptable answer, incidentally.
Okay.
Better, actually, than a number, in my opinion. But it's like leaving pi in your answer.
It's 1.3.
Okay.
Yeah, because it's just going to be, wait, if you don't leave pi or leave logarithm, it's just going to be a roundabout.
It's going to be rounded, but they didn't tell you how many places to round it to. Is it 1.3 hours or 1.35 hours or?
Now it says to graph the function.
Okay, but notice this is also a good ballpark figure. We know that in 1 hour it grew to 8,000. In an hour and a half it grew to 22,000. So the answer when it would grow to 15,000 must be between an hour and a half. So that's a good looking answer, 1.3.
Right.
Hours.
And can you use that to make your graph actually? Because couldn't x be your time?
You want to graph this. Okay.
Right, but if you used the way of plotting points, x would be your t.
Yeah, no, you're right. The horizontal axis is the t-axis. So
so this would be f of t.
When they say graph it, I guess they probably do want you to use those points. And the points were 1 hour, 1.5 hours, and 1.3. Well, we knew at 1 hour it was at 8K. So there's a point. At 1.5 hours, it was at 22K. And at 1.3 hours, it was 15K. So that's not very many points to graph it, but it's an exponential function. So we know
it'll obviously never be less than 1. It'll never be less than 0.
Time will never be less than 0. That's true. So what's this thing when t is 0? In other words, what's the y-intercept going to be?
It never reaches 0.
But what would it be? In other words, yes, it does reach 0. You know where it's 0? At the very beginning. How many bacteria did we have at the very beginning?
0.
1,000.
Oh, that's 0?
Uh-huh. So, the curve is going to start there, and then it's just going to have an exponential shape to it.
Okay.
In other words, typical exponential curve, if I just said what does e to the x look like, it looks like that. Well, this is going to be from here up.
Okay, that makes sense.
Okay, but all exponential curves look like this. It doesn't matter whether it's e to the x or 5 to the x or 100 to the x. It has this same kind of shape and appearance.
Right. Now,
this particular problem, it does not go to the left of the y-axis. because like you said, time can never be negative. But the rest of it's going to look very similar. The only point where we really, well, no, I think they gave you those 3 questions so that you could graph 4 points and draw the curve. And there were 4 points.
Right.
All right.
Okay, now this is the same thing, just like interest.
Okay.
So $12,000 is invested in a savings account, paying 5.6% interest per year.
Okay.
Write the formula for the amount in the account after T years if interest is compounded monthly.
Okay.
So 12,000.
Well, let's talk about, there's 3 formulas. Okay, you have to know all of them. Compound annually, compound more frequently than annually, and compound continuously.
Right.
Okay, so let's look at annual, just so you know it. It's your starting amount times 1 plus the rate of interest expressed as a decimal to the T years. Okay, that's if it was annual compounding.
Okay.
Now, greater than annual, meaning monthly, daily, whatever, the amount is equal to your starting amount times 1 plus R divided by some K, where K is the number of times per year it's compounded.
Right. I learned both of them the same way, just that when it was annually, K was 1.
Correct. And it is. And so this one ends up looking exactly like the top one.
Right.
And the final one is the amount equals PERT. And this R is, it's not 1 plus R. In other words, if this was being compounded continuously, we would use an R of 0.056. Okay? It's not. It's being compounded monthly. So let's erase this one. We don't need it anymore. But those 3 you want to always be able to recall when you need them for any particular problem. And from what you've given me, you're going to need all 3 of them because we've already done a continuous compounding. This is a greater than annual, and you are going to get an annual compounding question also.
So if it's compounded monthly, it's going to be 12,000 times.
The final amount is 12,000 times what?
1 plus 0.056 over 12 to the 12 to the 1.
12 to...
Yeah. Okay.
Okay, so there's our equation. And now they probably want to know what's your amount after some number of years. I don't know. What?
3 years.
4 years?
3.
I'm sorry, I still didn't hear?
3 years.
3 years. So it's going to be this. Let's go ahead and rewrite it. And, simplify it so that you can put it into a calculator.
12,000 times 1 plus 0.056.
Add those 2 together. The easiest way to do this is to come up with that number, add it to 1, and then I'll write that here.
0.056 divided 0.056 divided by.
You just did 0.056 divided by 12, right?
Yeah.
Okay. What is that?
1.004. It's 1.005.
Let's use more decimals than fewer because we're going to take this number and we're going to take it to the 36th power. So, okay, so accuracy could be very important. What's the rest of the decimals?
It's here. I'll do it again, but it was so it's one. So it's 1.00466666.
All right, now we got it. At least we got all the key ones.
Yeah.
And taking it to the 36th power was the reason I wanted as many decimals as not. I suspect that this number to the 36th power might be a few decimal places different than 1.004 to the 36th power.
Yeah.
But this is the one thing I would do next, and then multiply it by 12,000.
That's 1.1.
Okay, now take that whole number, multiply it by 12,000 before you round off.
So it's 14189.69.
All right, and you rounded that cents off?
Yeah.
Because dollars, they almost always want you to round it off to cents. Sometimes whole dollars, but never beyond the 9. So that's not very good, is it? 12,000 only grows to 14,189 after 3 years at an interest rate of 5.6%, which is a great interest rate. You can't find anything close to that anywhere now.
Right.
And that's compounded monthly. Now, if you were to do the math and figure out what this thing would be if you compounded it continuously, not going to be that big a difference. You might think it might be, but I'll bet it's no bigger than that. In other words, if I
Does
did...
compounding give you more money the more often you compound?
Yes, but there's a limit on, what do I want to, the word I'm looking for. In other words, compounding, the difference between compounding daily and compounding continuously is almost nothing. The difference between compounded daily and compounded yearly is significant.
Okay.
And you can kind of see that here. In other words, if I take 5.5% of 12,000, it's only $600, $700, and I add it to that, and now the next year I take 5.5% of $12,700, and I maybe come up with 13,600, something like that. Okay, so if I'm compounding it annually, it's not going to be that much. So compounding it monthly maybe gives me an extra 500. I just did rough estimates in my head, but so there's definitely a difference.
Okay.
And the reason they use continuous compounding in things like bacteria growth is because bacteria grow continuously based on how many there are there at any point in time. Notice that money does not. Your money is specifically compounded once a month, not continuously.
Okay.
Okay. But natural processes are almost all continuous. In other words, when you're talking decay, when you're talking radioactive decay, it's a continuous decay. And whenever you're dealing with continuous, you're always going to have the number E involved.
Right.
All right, what else?
Let's see.
It should set you pretty good on logs and exponentials.
Yeah. Okay, let's get this over there.
What's some of the other subject material that's going to be on your test? Because I generally have a pretty good feel for what gives students trouble and what doesn't. And certainly logs and exponentials are one. That didn't surprise me. Trig? Are you going to be tested on trig?
Some trig.
Just some? Okay. And the basic one? The basic trig? Basic identities, not like trig equations or anything?
What do you mean by trig equations?
Sine squared x equals cosine x minus 1, something like that, or plus 1.
Yeah, I think we're going to be testing on this.
Okay, might want to go over some trig equations if you can find some. I don't want to make them up because I might make them up much harder than you're going to be tested on. I could make some up, but identities, trig identities, maybe that's what we should review.
Okay.
Because you're not allowed a cheat sheet, right? Am I correct? No. And they're not going to give you any of the identities? So, absolutely. The best thing we can do with 20 minutes is to review your identities. There's 11 really key basic identities. Starting out with the 6 reciprocal. 6 reciprocal. What's sine's reciprocal?
Sine's reciprocal.
I'm going to leave off the x, but I shouldn't, because it's important to know that when you use a trig function, it's of an angle. Right. There's never a sine without an argument. Okay? So I'll put it in just so I don't mislead you. So the sine of x is equal to what its reciprocal?
And that's sine is
it's either cosecant or secant, right?
Yeah, it's cosecant.
It's different first letter always, S and C. So that also means the cosecant is 1 over the sine, right? So the ones on the far right, you don't really have to write those if you were going to make a cheat sheet of your own. You'd only want to, let me just show you the ones that you have to kind of memorize. You don't need to memorize the ones on the right because you can always figure those out. What's cosine's reciprocal?
Cosecant. I mean, no, secant.
And tangent's reciprocal.
Tangent's reciprocal is cotangent.
Okay. So there's the 6 reciprocals. Must know those. There are 2 quotient identities. One being tangents. What's tangent's quotient identity?
Quotient?
Mm-hmm.
Cotangent?
One trig function divided by a second trig function.
Sine over cosine.
Sine of x over cosine of x. And the other one that you need to know is cotangent. Well, let me put that on the right because you don't need to actually memorize that. You can always figure that out. Since cotangent's the reciprocal of tangent, what's it equal to?
Cosine over sine.
And finally, there are 3 Pythagorean identities. Starting with the most important one, sine squared x plus cosine squared x equals what?
10 squared x?
1.
Oh.
No matter the angle, always 1. Okay. Now, it couldn't be 10 because sine of x can never be outside the range of 1 to minus 1. Okay, so the biggest this number could ever be would be 1, squared even. Because if it's less than 1 and you square it, it's going to get smaller. Same thing with this number. So their combined total, it'd be impossible for it to be more than 2, but it's actually impossible for it to be more than 1. It's always 1. I can put a 29-degree angle in there. I can put a 77-degree angle in there. This is true, always. Okay? And there's only one more you have to memorize, involving tangent squared. What's the rest of this one?
Plus sine squared.
Plus 1 equals secant squared. Okay? Notice how much different it looks. And then the third one involves the cofunctions of the second one. So what is the third one? In other words, the third one looks exactly the same as the second one, only it's the cofunctions, not the functions.
So it's cotangent.
Cosecant. Nope, my mistake. Cotangent squared plus 1 equals what?
Cosecant. No, equals cosecant.
Cosecant. There's a difference between cofunctions and reciprocal functions. These are reciprocal, okay? A cofunction is the function with the word co in front of it. In other words, the cofunction of sine is cosine. The cofunction of secant is cosecant. And the cofunction of tangent is cotangent. And the cofunction of cotangent is tangent. So it's both ways, but you don't really have to write those out because it's just the function with the word co in front of it.
Right.
So of these 11, these are probably the only 11 that you're going to have to memorize, that you're going to have to know, is my guess. I don't know. I can mention a couple others and you tell me. But notice of these 11, I only have to memorize 3, 4, 5, 6.
Right.
And then I can figure out the other 5. Okay? Now, there are some other, tell me if you've heard of this. That's the cofunction property. And all cofunctions share this property. In other words, tangent of x is equal to the cotangent of 90 minus x, and same with the secant x equals cosecant 90 minus x, and it works the other way also. In other words, cosine is equal to sine of 90 minus x. Okay, so these are the 6 cofunction properties. Did you deal with this at all when you went through trig?
I don't think so.
Yeah, not everybody does. This is...
But you can kind of assume this when you have to graph the quadrants of things.
Yeah, not so much, but it depends whether they give you a problem. They might say, I don't know, they could have any number of problems that would require you to know these functions. Okay, but if you look at it, the sine of 30 degrees is equal to 1/2. Well, the cosine of 60 also has to be equal to 1/2 because the sine of 30 is the same as the cosine of 90 minus 30. So the sine of 30 has to be the same as the cosine of 60.
Okay.
So there's all kinds of problems they could give you that would require you to know this. But not all trig students get into the cofunction properties. So I don't want to take up space in your memory with stuff you don't need. However, you might need sum and difference. Maybe not. A plus or minus B, and sine of A plus or minus B. That one's cosine A, cosine B, minus or plus sine A, sine B. Familiar or not?
No.
Let's not do it then. Because there are, I mean, if you take another trig course, there's maybe another 15 to 20 identities that are important to memorize. Things like sum and difference of angles, things like double angle. What's the sine of 2x? Well, that's the 2 sine of x cosine x. You probably haven't had that either. Double angles, half angles, sum and difference of angles, things like that. So what kind of trig problems? We still have 10 minutes. We've reviewed the identities. Now let's do some problems that you might get on your test. I don't know if you can go to your review material and go to the trig section or what, but
I can.
did you have a review packet or are you just going through?
Well, I have my book, and he gave me what to review. Okay, wait. Here's one. Cosine of the parenthesis tangent for the -1, which is just cotangent. Parenthesis, open another, negative square root of 3, and then close parentheses.
Okay. So you've had inverse trig functions, and let's talk about inverse trig functions for a moment. We always take trig functions of angles to get ratios. We always take inverse trig functions of ratios to get angles. Very important thing to comprehend.
Okay.
So if I give you a triangle and I say solve for an angle, you're going to have to use an inverse trig function at some point in time.
Right.
Okay. When you have a combination like this, where you have cosine of the inverse tangent, well, we have to start from the inside first. And, in your calculator, go ahead and put inverse tangent of -√3.
Inverse tangent of negative.
And make sure you know if your calculator is in degrees or radians. Do you know immediately or not?
I don't.
Okay, here's how you can test it. Do the sine of 30. If you get 1/2, you're in degrees. If you get anything else, you're in radians.
Sine 30. Yeah, I got -0.988.
Okay, go to your mode. Go down to where it says degrees or radians and make sure you highlight degrees. And that's how you change it, from radians to degrees.
Okay.
But if you don't know, there's no good place on there where it tells you. You would think that every time you put a trig function in there, they'd say, you're in degrees or radians, but they don't.
Yeah.
Now do sine of 30, make sure you get 0.5.
Yeah, I got 0.5.
Okay. Now do inverse tangents of -√3. It's going to give you an angle.
Negative 60.
Correct. And it's going to give you a negative angle because it's negative tangent. And your calculator is always going to give you either a first or a fourth quadrant answer when you put in an inverse tangent. Same thing with inverse sine. You're getting the first or fourth quadrant only. Because it's also negative in the second quadrant. But notice it didn't give you the second quadrant answer. It gave you the fourth quadrant answer.
Right.
Now, type cosine of negative 60.
0.5.
Correct. And that is positive. And there's a couple of other trig properties that they may or may not have told you about, and that's the odd-even properties. Let's just talk about it for a second, because it's pretty important. Both sine and tangent are odd functions. In that the sine of negative x equals negative sine of x. Tangent of negative x equals negative tangent of x.
But cosine of negative x equals cosine of x.
Correct. Cosine is an even function, where when you substitute negative x, it doesn't matter. You still get cosine of x. So I could have applied that here and just said, well, the cosine of negative 60 is the same as the cosine of 60. But you're doing it in the calculator anyway, so it doesn't matter so much. But did they teach you this odd-even properties of these?
I think you did, actually.
Oh, okay. Okay. Well, again, I hate to almost give you anything beyond what your test is going to be on.
No, but that could be helpful on the test.
Well, it is kind of helpful sometimes because
he is the type of teacher that will test us on anything in the chapters, even if he didn't teach.
In other words, if I said, if you're using your do you get to use your calculator on the whole test?
Yeah.
There's no part of it that it's a no calculator test?
Nope.
Good. Good. That should help with a lot of these trig problems.
Right.
In other words, you wouldn't need this at all since you're using calculator on all these problems. But it is important to understand that when you take the inverse, you don't get both quadrants out of your calculator. In other words, the sine of 30 degrees is equal to 1/2, and the sine of 150 degrees is also equal to 1/2.
Right.
But the inverse sine of 1/2 is always going to tell you 30 degrees. It's never going to give you this answer from the calculator. It's never going to give you the 150 degree answer, even though it is correct. The inverse sine of 1/2 is also 150 degrees. It just...
But isn't that with all angles?
What's that?
Isn't that with every single angle? There's two co-angles?
Yes. They're in the unit circle there. But I don't even need to stop there. It's also equal to 390 degrees. In other words, I go on forever.
Right. And it's just depending on what you subtract it from.
Yeah. Now, actually, there's one really, really important thing that you need to be able to do with trig, that for sure, and that's how do you get that? Well, you can use your calculator on those also. I mean, there's no portion of the test where they force you to do problems like this without a calculator?
Nope. There was earlier in the year.
Okay, I was going to say, boy, there should be. Because when they teach it, they want you to know all of these angles that are multiples of 30, 60, and 45. They want you to know how to get that without a calculator.
Right.
Okay.
And they did earlier.
And let me just real quickly, in the last 2 minutes, quickly draw our unit circle and put, this is quadrant 1, 2, 3, 4. And when you're dealing with angles in the second quadrant, it's 180 minus x. When you're dealing with angles in the third, it's x minus 180. And when you're dealing with angles in the fourth, it's 360 minus x.
Okay.
So if I said to you, what is the sine of 225, what's the reference angle going to be? In other words, the equivalent first quadrant angle.
For 225?
Use that formula right there.
It's 45.
Yeah, so I'm really talking about the same number as the sine of 45. Well, that's square root of 2 over 2. Hold on one second. Sean? Hey, I'm finishing up a session. I'm done in 1 minute. Just hold on, will you? I'll be right with you. All right, hold on. Max, I'm going to let you go, okay?
Okay.
Make sure you know how to do all 4 of these quadrants. In other words, any angle that's in any of the 4 quadrants by applying these formulas.
Okay.
And then all students take calculus to put the sign on it. Well, the sine of 225 is not square root of 2 over 2. It's minus because that's in the 3rd quadrant.
Right.
Sine is negative in the 3rd quadrant.
Right.
All right.
Okay.
Have a good one, and I'll talk to you on Monday.
All right.
All right. Bye-bye.